Hello. So let's talk about optimization today. I was going to do bricks, but I think it's probably a better time to do optimization. We've got this terrain, right? And a lot of you have probably started to encounter the 65,000 vertex limit if you've been playing around with chunk size. The chunk size is the 65,000 vertex limit is a hard limit, but it's not something you should be encountering just yet. If you are encountering it, you're probably not culling your faces correctly, because this is a huge chunk, okay? And it only has 33,000 verts. So I mean, it's a massive chunk and it's only halfway to the limit. And even if we were to upgrade it from 40 to 50 by 80, for example, 50 by 50 by 80, now we should be starting to encounter, yeah. So now we've got a couple of chunks that have failed. Um, and these chunks are pushing it even though they're quite flat. So we can optimize a few things from this. The first thing we can optimize is we can take off this bottom. It serves absolutely no purpose and is very easy to get rid of. So let's go ahead and do that. Here we say is transparent. We just say if y is less than 0, return false. So we say that the ground beneath the world is always going to be opaque, so you don't have to draw it. And you can see that, come on, you can see that now the underside of all of these is no longer being drawn, and that'll save you some. The other thing that you might notice is we've got these massive walls, and this is where we have to start to consider optimization much more critically. Now we can in fact determine whether or not we want to draw those walls, and I'm going to show you how to do that. So we can go into this get byte, and right now we say get byte. If it's not on ours, it's automatically a 0. Well, we can actually search for a chunk to find a chunk that we're actually going to get. So let's go ahead and do that. First off, we have y here. This y value, we are not stacking chunks vertically. So if we're searching for a y value and the y value is outside of our limit, then it's legitimately outside of everyone's limit. But the x and the z, we can actually grab those. So let's go ahead and create a new position. And then we're going to add our transform position to it. And that gives us the world position of the brick we want. Now we need to go ahead and get the chunk that is in that location. And now if chunk equals this, return 0 because that's some kind of weird error. If chunk equals null, return 0 because it doesn't exist yet. And otherwise, return chunk.getByte world pause. Now, if you have been paying attention or if you're following along, you may have noticed I just passed getByte a vector 3. That's because I went ahead and I created another function. This is the second take and I didn't delete this function. This is a function which just translates a world position into a local position. All it does is take the world position and subtract our location from it, and then floor every one of the 3 components and then return getByte. So all that does is translate a world position into local position so that we can grab the correct byte. So now when we hit play, you can see that we still have some opaque walls, and the reason for that is because right now we have this situation where we say if there is no chunk, then it's transparent. Let's go ahead and say if there is a chunk, if there is no chunk, then return something that's opaque. So now you can see that we don't have any walls here. We've said that if there is no chunk there, it's opaque, you don't have to draw anything. But the problem is that when we go exploring, there's an example. When we go exploring, the chunks load up asynchronously. So this chunk loaded up, and it looked over at this chunk, but at the time this chunk didn't exist. So this chunk said, oh, well, all of these blocks are opaque, so I don't have to draw anything. And when this chunk popped into existence, this chunk didn't redraw. It just kept what it was, which meant that now that there was a chunk there, it was incorrect. Now if we look at this chunk here, we'll find that it is correct in terms of what it draws because this chunk already existed. So those are the sorts of, there's another big example right there. So those are the sorts of examples you're going to run into. These chunks don't always all exist, but we do have a couple of options. One option is we could try and recalculate all of the neighbor chunks every time we create a chunk, but our mesh is already really slow to recalculate. The collision mesh, painfully slow. So let's not do that, because that would require us to do 3 times as much mesh recalculation. Bad idea. Another option, however, is that we can simply ask the chunk what that brick would be if it existed. You have to remember that we are using a seed value here. You see? You got all this stuff here? So what we're going to do is we're going to go ahead and create a public static virtual byte get theoretical byte, and then we need a position. Okay, so when we do that, we need to have this same stuff, but we're going to be doing it just for 1 byte. So let's go ahead and do it. We need the seed, we need the grain offsets, all that stuff is still correct. And then here, we're not going to walk through XYZ, we're just going to go ahead and grab it and calculate it. But that means that there's an opportunity here to actually just do this part outside of the function. So let's create another function, public static virtual byte get theoretical byte, and it's the exact same thing, right? Except we're putting this stuff in it. So we're telling it to go ahead and get the theoretical byte. But you notice that there's some things that we're missing here. We don't need that, for example. But for example, we've got this thing where we have the grain offsets and that sort of stuff, and all of that stuff is actually handled sorry, there we go. So we've got a couple of things up here like the grain offsets and stuff that is actually still being handled down here. So let's just cut it out and stick it up here. So what we actually are doing now is these grain offsets are being calculated here, and I just copied them and pasted them without thinking, and I was wrong. They need to go here, because the whole idea is that they happen directly after the random seed. So we need to actually pass those grain offsets in as arguments. So let's do that. Like so. And we just go ahead and replace these with the correct ones. It doesn't really matter which ones, they're all the same from that perspective. There we go. So we've just kind of split up the functionality a lot, which allows us to call this get theoretical byte whenever we need to. And one of the things that we're going to use that for is here, we're going to go ahead and call it again. There we go. Alright, so I'm hoping you understood what we did. We took some of the functionality from calculate map from scratch, and we separated it out into get theoretical byte. And that allows us to actually get that map value even if the block hasn't been pulled into existence yet. We mathematically already know what brick should be there, so we might as well go ahead and be able to just get it. And therefore, when we're down here in our get byte, when we say chunk equals null, we're actually just going to go ahead and say to return what it should be. Like that. Oh, sorry, you can't have, just going on autopilot there, you can't have virtual statics, you can't override them. That should be obvious, I'm just being stupid. Okay, here we are. An object reference is required to access calculate noise value. Calculate noise value shouldn't be, this should be static. The reason I didn't want it static is because I wanted to be able to override it, but screw that, I don't really care. One more bug. If mountain value is greater than y. Well, in this case, what we actually mean is pos.y. Alright, so you can see that we've got this nice mountain going, and I don't see any flaws in our script, or in our system, even though this would be where they would be if there were going to be any. So you can see that this wall here this face is correct, this face is correct, and we can walk around and summon up a couple of these. Let's go up the mountain, that way we'll have a downside, a down mountain, a downhill area. Those would be where it would malfunction. That would malfunction. Let's go ahead and take a look. Did that malfunction? Where are we? There we are. Nope, it's perfect. So that is how you optimize your meshes at this level. There is another level of optimization that we will be discussing later when we are doing optimization specifically for optimizing our collision meshes. Because the collision mesh is awful. It's slow as hell. And we're going to get to that, but not today. This is enough for today. You know, I may go ahead and do the collision mesh optimization next time. We can just get the optimizations out of the way in one double pack. So I hope you enjoyed this episode, and don't worry if your terrain doesn't look like mine. It doesn't have to. Make it look like whatever you want. I've chosen this kind of terrain because mine takes place in space, so the low gravity would arguably result in those kinds of blobby high mountains instead of actual worn terrain. Whatever. Anyhow, that's one level of optimization, and you can see that even this really, really complicated mesh only pulls in at 30,000, and that is a massive mesh. That is a 50 by, what is it, 50 by 50 by 70, 50 by 50 by 80, and it's mostly wall with floating stuff. That is a massive chunk, and I'm not pushing the 65,000 limit. Alright, so next time we're going to make it so that it doesn't take eternity to actually do our calculations for collision meshes.